The Warren Lecture Series. Today we have a guest speaker from Germany, Professor Benjamin Klusemann. He is an associate professor of Leuphana, University of Luneburg. I hope I do it right. Dominic is not here. No one is laughing. Benjamin studied mechanical engineering at Technical University of Dortmund, and he was also an exchange student in USA at the University of Idaho. He did his PhD also at Technical University of Dortmund, and he graduated in 2010. After that, he was a postdoctoral fellow in Aachen, Germany, and in 2012 he moved to Munich, where he joined Institute for Continuum Mechanics and Material Mechanics as a senior researcher. Then he got a Humboldt Fellowship and came to Caltech in 2013, working with a group of Kochman and Ortiz as a postdoctoral scholar. And since 2015, he is a professor, associate professor at University of Luneburg. And he has a number of awards. One of very distinguished award is von Mises Prize, which he just got, I believe, in 2017. He also has teaching awards, and his research interests are topics in micromechanics and multiscale modeling and more. So I would not take more time and give floor to Benjamin. Please join me in welcoming the speaker.
Yeah, thank you very much for this nice introduction, and of course thank you for that I can be here today and present some of my work which I did in particular over the last 3 years, but also some current topics which I'm working in my new position, which I have here also at the Institute of Materials Research at the Helmholtz-Zentrum in Gesta. So I have actually a shared professorship, it's called in Germany, so both institutions are actually paying half of my salary if you want to. Okay, so the title of my talk is today Numerical Modeling of Heterogeneous Materials in Technological Process with Experimental Validation. As I heard, the group is quite heterogeneous, as also in the title. I try to not give too much formulas, so more kind of a lot of pictures and give you some ideas what we're actually working on, and maybe there's later on a chance to discuss these. So why are we actually interested in heterogeneous materials? Well, here are just some examples. So first of all, some micrographs, for example, of different thermal sprayed coatings. And you can see here, here in particular, we have the same material composition. However, based on the process they are processed, so one plasma spraying and one high velocity spraying, you see completely different microstructures. And of course, if you take a completely different composition, you have, of course, also some heterogeneity, which is very different to the other pictures. Another example are here particle reinforced metal matrix composites, so silicon carbide particles in aluminum matrix. And also if you're doing sintering or if you're doing material alloying, this results in a different heterogeneity of your material. So you have to account for this somehow in your material model to predict the macroscopic properties correctly, also your structural properties, of course. But there is also another heterogeneity which I worked in particular on during my habilitation, which is the heterogeneity from a developing microstructure. So you don't have a constant microstructure coming from the production process or the composition in advance. You have a heterogeneity coming from developing during the process actually. So some example is here, for example, Lüders band development in steel. So you can understand it in the way to have initially a homogeneous distribution, but then you have a strain band which starts here. And this strain band then takes over in principle the whole macroscopic deformation you have at that time and runs through your sample until the Lüders band ends, and then you have again a continuous distribution. Other example is here, for example, a twinning microstructure, or here some microbands in copper, which simply means that rather than the material would deform homogeneously, you can just imagine like a tensile test, you pull on it, and you would expect everything is deforming similar way. Now, in this material, it happens that you have these microbands, which implies regions of high and low plastic strain, which is energetically more favorable rather than having a homogeneous distribution. And I think this example probably everybody knows is the dislocation microstructure in nickel. So rather than having also a homogeneous distribution of this dislocation, you see this very typical dislocation cell structure. So these kind of mechanisms have to be accounted somehow in your material model to predict the properties, of course, correctly. Well, I, in particular, in my new position, I'm dealing always with applications. So this has to be always remembered in background. So here, just some example of some deep drawings, for example, or also of some forming in general. And this has to be taken, of course, always into account. So it's not enough if you just account for a very small part of your material. You want to apply this also to large process simulations in the end. So you need some technical tools for that. So when we want to understand the material behavior, we always come to multiscale. We just were in the seminar before, also multiscale. This is, of course, a very urgent topic. You can understand that if you just look here at this cup. You have a specimen on the beginning. You zoom in principle in, and you find at the first level maybe a polycrystal, then a subgrain dislocation structure. You go even further down, you find maybe dislocations, then the single lattice defects, and at the lower scale, of course, your atoms. So you have several length scales here, but not only length scales, you have, of course, also several time scales. And well, you could, of course, now say, okay, it might be optimal just to start with the atomic level. You discretize everything with single atoms, and then you have your specimen properties correctly. Yeah, first of all, this is numerically not possible to handle. And additionally, it's also a question if you not introduce a very, very small error at this level, which actually sums up at the higher scales. So there's always needs for models which are, first of all, coupling these information. But also to have actually models which start at higher levels and actually incorporate this in a kind of homogenized way, your properties from the lower scales. So which you can also validate then with experimental results, for example. Okay, so the first topic I will talk about is related to size effects. And size effects, when you think about that, you classically think about a Hall patch effect. However, this is not what I'm talking about today. So just imagine the following case. So you have the classical miniaturization, which leads to even thinner and smaller metal components. But this doesn't mean that your grain size has also to be decreasing. Of course, if you're talking about nanocrystals, this is true. However, in general, this has not to be the case. It just can be the case that your specimen size is decreasing. And if you have this case, then of course you have much less crystals present, and this leads to a dramatic change in your mechanical properties. So what I will talk about is first order size effects. So as I mentioned, first order size effects are first of all the microstructure size effect, so classically Hall patch, which simply means as smaller my grain size gets, the stronger my material. It's related to the dislocations. What I'm talking about is the so-called statistical size effect, which is often forgotten, and that's just shown here. So you have your tensile specimen, and imagine the case you have a large number of grains here, and you have an isotropic orientation, isotropic texture, let's say. Then it actually doesn't matter what the single orientation of each of the grains is. You have always a kind of similar response if you do tensile tests on these kind of samples. However, imagine the case you have in the extremum just one grain over the width or even over the thickness. Then of course your material macroscopic response is strongly related to the orientation of each single grain. No? You have a very high heterogeneity of your answer. Also you would say, well, the material in general has an isotropic texture. Okay, so what we did here was an investigation of a so-called oligocrystal. So oligocrystal means a sample with very few and large grains. This was an iron silicon oligocrystal, so it's mainly a model material, I have to say, which allows to produce these kind of samples. And from experiment we obtained then first of all the grain orientation with basis on EBSD measurements, as well of course on the grain morphology, where we approximated here always the surfaces, in particular in thickness direction, to be orthogonal to the surface actually. So this results then in this final element model, and the real sample looked exactly like this. Now of course the approximation of that is normal to the surface. That was an approximation, but it fitted quite well to the experimental results. Then we implemented, of course, a material model for this, which is in principle a classical crystal plasticity model. So what you see here is first of all the plastic velocity gradient, which is simply the sum of all the slips on each of the glide systems. No? So this is classically the slip direction, and this is the slip normal. As we're working here with large deformation, we have, of course, the evolution equation here for the plastic velocity, simply given by the plastic velocity gradients times Fp itself. And then we have, of course, evolution equations on our single glide systems. So iron silicon is a body-centered cubic, has a body-centered crystal structure, which means it has 24 glide systems. And these were incorporated then in principle for each of these. We formulated this kind of material law, where we have, of course, here classically our Schmidt stress. This is simply the projection of our stress, of our global stress, macroscopic stress, to our glide system level, 24 of them. And then we have an evolution equation for this dissipative strengthening mechanism, or dissipative hardening, which is here given by this equation, which simply accounts for the hardening on the glide system itself, but also contribution coming from other glide systems. So kind of self-hardening and latent hardening, which is accounted by this matrix. This is the classical picture which you always see here. Okay, so what we did first, we investigated the deformation field. And we had the problem for this iron silicon, we didn't really had enough material data, to say. At least not from the single crystal level. So what we thought, well, let's see, first of all, what is the influence of the initial orientation of our grains. So what we did is we assumed an ideal crystal plasticity model, so no hardening on the glide system level, just an initial strength, initial yield strength, and of course we're accounting for the orientation of each of our single grains. So on the left side you see the experiment, and the red lines, this is approximation of the deformation field to have a comparison to the simulation. And what you can see here on the right is then the simulation results in black, and of course in red is the experiment. Well, no, other way around. Let's see. Yeah, it's right here. And what you can see is that on the beginning, well, you cannot see really a difference. It looks that we initially captured the deformation correctly. However, as soon as the deformation gets large, and we assumed here an ideal crystal plasticity model, so no hardening, we see a large deviation, and in particular we see also that we get here in the simulation a kind of necking behavior in these kind of grains, which represent this one and this one. This was not the region which showed in the experiment the largest deformation. So there's a wrong, I name it simply necking, prediction in this kind of model, but this was also not surprisingly, as we assumed an ideal plasticity model. Okay, so we just went then a step further. So we included now the hardening which we identified on material data from the literature. And what we could see is, first of all, we get a very good agreement until 10%. It's very excellent in this sense. And also to 20%, we see at least the correct tendencies. However, we underestimated here now the necking phenomena in the simulation compared to experiment.
So there's no calibration here. Sorry. There's no calibration.
There's only calibration regarding the material properties. Yeah, the material properties have to be identified. There's no further calibration on the model, no. It's just a single crystal model which is identified on material data, applied to the oligocrystal, but there's no identification process. So this was our partners, which we did in particular with the University of Saarland, so Horst Wehoff did the experiments. They were really surprised that we could predict this without any specific identification already quite accurately. And this shows already that a simple crystal plasticity model is very accurately in predicting actually the deformation, which was very interesting to see for this kind of material. However, we of course as mechanics, we were still interested in see why. Why is this actually here showing this deviation? And I mean, this is also a very, well, this is a quantitative comparison, but only with respect to deformation field. And we had more information, of course, from the experiment, so let's go one step further. So what we did next, we identified, we compared the so-called orientation gradient. The orientation gradient is a kind of measurement for the dislocation density, because dislocation density is very hard to measure, as you can imagine. And but you can understand the orientation gradient as a kind of local misfit, or it's a kind of local incompatibility, which is similar to something like dislocation density. It's not exactly the same, obviously, but you can at least compare the tendency where you have the highest development. So orientation gradient is simply calculated based on the misorientation between two neighboring pixels in the experiment, or in the simulation, two neighboring Gauss integration points. So you just take the orientation which you have, and of course you're accounting only for your grain alone, not over the grain boundary, because there you have large misorientations, just inside of the grain. And then of course you minimize that with respect to all crystal orientations, and you're plotting here the maximum in x and y direction. Simply on the surface you can do that. At least in the experiment simulation we can do volume-wise, but we compare here only the surface one. So on the left you see the experiment, and what you can see in particular that we have some local regions where we have large orientation gradients which appear. And interestingly was that in this region where we saw the necking kind of behavior, largest contraction behavior, we nearly didn't see any orientation gradient developing, which implied for us at least that there might be some hardening mechanisms related to dislocations, so geometric dislocation, that take place in this region where this part it's softer than the remaining part, and we would get there kind of stronger contraction. So first of all, we compared this, of course, to the results of the simulation before, which you can see here. And interestingly is that we saw some similar tendencies. So here you saw a strong band, which you can also see here. And also this region, which shows a kind of high orientation gradient, was also predicted by the simulation. And we thought from this point of view that a further G&D-based kinematic hardening would lead to a slight improvement at least, which we also investigated then based on a non-local model formulation. However, I have to say the grains are already so large, 2 millimeters approximately the grain size diameter, that the effect was not very large. So it didn't. We had an improvement by 3%, which we measured. So this is not really much helping, but we could see it. There was some improvement. Okay, so by that I will go to the next topic actually, which is the so-called Porte-Vanneau-Chatelier effect. The Porte-Vanneau-Chatelier effect is a kind of material instability which is related, of course, also to dislocations. And you can in principle imagine it in a way that you have an alloy, a pure alloy in the beginning, and of course you want to strengthen the properties, so you just name it this way, you have additional alloy elements in it, in this case magnesium, and this might lead in specific region of strain rate and temperature to some local instabilities, which then results in these so-called Porte-Vanneau-Chatelier effects, or bands. This instability is usually attributed to dynamic strain aging. Imagine it like this way. So you have these solute atoms inside of your material. Then you have a number of dislocations. They are attracted by this solute atoms, and then they are stuck there for a certain time. So there's somehow a kind of a cloud, I would say it. And you need you need to overcome a certain stress level, and then this cloud is released, and you have these bands then inside of your structure. This is of course then the interaction between the mobile dislocations and solute atoms. It's always the mobile dislocations. So usually you classify these PLC bands in 3 types. So you have first of all the type A, which is a continuously smoothly running PLC band. You would see that when you look at the stress strain curve, like this classical step stair structure, and when you look at these kind of images, you see in principle a band which running through your whole sample. This is type A. Type B shows a more oscillarity behavior in the stress-strain response, and you have an intermittent propagation behavior. So you have a PLC band which runs through your sample, stops, disappears at the same position, appears again at the same position. And then type C is a kind of stochastic nucleation, so it's very, very hard to predict. And this strongly depends, of course, on your temperature as well as on the strain rate and also on the strain level actually inside of your material. Okay. So we investigated that again from experimental point as well as numerical point. So here you see our experimental setup, which is just principal mini micro tensile specimens of this size. So every diameter is here given in millimeters. And the important thing is here that we have actually a gauge length of only 2 millimeters. Why did we choose such a small length? Well, the reason was that we wanted to avoid to have more than one PLC band in our sample. We just wanted to have one PLC band which we can then distinguishably detect based on the thermocamera as well as on strain gauges. That's why we used such a small local region. From that, we set up, of course, a finite element model, a bit simplified here, and of course, we had to take care of the mesh density inside of your of the interesting region because we're using a local model. We don't use a non-local model, we're using a local model, so we have to be taking care of the mesh sensitivity. Our material model is based on continuum thermodynamics, so everything is related to energetic and dissipative effects. And for that reason, we formulated here our free energy density, which is here very classically just the elastic part with accounting for temperature effect, plus then some hardening contribution. And from the hardening contribution, we simply assumed a kind of Voscher hardening. Then, of course, we have the dissipative effect, which is given here by the dissipation potential. So we have a classical activation form, plus then this power law relation in terms of the plastic strain rate, plus a term which is now contributing to the PLC effect. This is a Cottrell-Allure-Bilbey stress contribution. And this one is in principle was the key for predicting also the so-called inverse strain rate sensitivity dependency, which I will show in a minute, which means when you have classically, when you decrease your strain rate, so you first have at high strain rates you have type A behavior, you're decreasing, then you're coming to type B, type C, and usually also your strain for initializing the PLC effect is decreasing. At a certain strain rate, when you're low enough, it should also increase again, and the classical model, or this is the classical model coming from Estre and Mekonic. This didn't account for that, and an extension from Böke was then to account here for this linear contribution of the stress onto the strain itself, and with this we could actually capture this phenomena, which I will show in a minute. So this is in principle the central equation for this PLC effect, where you have this TA, which is the so-called aging time, which of course depends on a waiting time. In principle, a dislocation has to wait at these solute atoms, which is then depending here on this function omega, which is again a function on the strain itself. So this was incorporated into Abacus as a user material. And first of all, we had to identify, of course, some material parameters. This was the first step we had to do. So we compared we identified our simulation based on experimental data for a number of different strain rates. And what you can see here is from the very low strain rate, where you have a kind of very oscillatory behavior, it gets much more to this kind of step-stair structure. And this is also predicted by the simulation accordingly. One important thing which I just mentioned is this plot where you have the critical strain over the strain rate. First of all, you see of course that we have this decreasing critical strain with decreasing strain rate, but then also the inverse behavior, so we have an increase again of the critical strain with further decreasing the strain rate, which is not classically done by these kind of models. So usually they show this behavior which is this way, just always decreasing. So first of all, we could show that by identifying the material parameters correctly, we are able to predict the macroscopic behavior correctly, and we are also able to predict this transition between the different modes, different PLC bands, from high to low strain rates correctly. And I will show you in a minute that it's actually also true for low to high strains, because there we have also an additional change. Okay, so here, So here you simply can see a comparison now. On the left you see the results of our thermocamera, which were, the experiments were done in Dortmund. And on the right you see the simulation for one specific strain weight. And what you could nicely see is, of course, we have sometimes a PLC band which runs through it, but sometimes also disappears. So here we have a continuous band now. We see something similar like this. So this was a strain weight which was intermediate between A and B. This was a kind of mixture, just to show how we obtained actually some results experimentally as well as numerical-wise. Okay, so first of all we investigated the nucleation behavior. That was the first step. So on the top here you see some experimental results. The time step between these different pictures is 0.07 seconds. The same holds for the simulation. Of course a different time step, but different time stage, but the time shift is always the same. And what we looked here was in particular how actually the PLC band behaves during the nucleation with respect to longitudinal and transverse propagation. And what you could see from the experiment very clearly was that we have, during the transverse propagation, we have already a kind of behavior with respect to the longitude direction. So the PLC band does not be completely formed already until it already starts to move actually inside of the sample. And kind of similar we saw here. Here it was a bit more stronger, but here we also saw we had a starting point, and then also the middle point actually was already shifted a bit, and then it continues, of course, to propagate. And we could, of course, then investigate the stress strain level, and the starting point of the nucleation was then mainly attributed to a large drop in terms of the stresses. When you have the PLC band starting, it's dropping strongly, and then starting continuously to increase. Okay, second of all, we investigated then, of course, the band propagation behavior. Here is first of all the experiment shown. Here you see in the background always the kind of images from the PLC band. So they always take one slice out of each time step, and we could see by this that we have here a very nice continuously propagating PLC band in the experiment, which is also nicely attributed. Look in particular at the green line, which represented the strain level. We have this very classical step-stair structure. Every step is correlated to one PLC band. And as soon as we go to larger time steps, which means of course also that the strain is increasing, we see changes in these PLC bands. So first very continuously, and then later on it already sees there's some broken point, and later on you completely see they starting, stopping, appearing again at the same position, propagating, and the same happens. And we have also much stronger oscillations, so classical type B behavior. So this shows of course that we have this transition from type A to type B, not only with decreasing strain rate, we have that also with increasing strain. And the same we investigated of course with the simulation. Here on the top layer you see a classical type A band. So here we have a band which starts running through it and then continuously propagating, where here later on we have a PLC band which starts also then changing during the run through the through gauge region. We have even changed orientation, which we also saw experimentally, and so our model was also able to predict, at least in the tendency, the transition from type A to type B for larger strains correctly. Then we quantified this also a bit in terms of band characteristics. So first of all, we investigated the band velocity, and what we saw in particular in the experiment, it was a bit stronger, that we had a decreasing velocity with increasing strain, also for each of the PLC bands. But on the beginning, we had a short increase. Just for 2% until 1% strain, we had a short increase of the band velocity, and then it always decreases. When we now take the average of the first, I think it was 10 PLC bands, then we saw the tendency, of course, that the band velocity increases with strain rate, or of course decreases with decreasing strain rate. Additionally, we looked at the jumps. because we wanted in particular to have an investigation how strong is this jump strain rate dependent. And what we saw, well, there was nearly no strain rate dependency, so the jump was always the same. But we saw a strong dependency regarding to the strain level again, which also somehow explains this kind of change in terms of the PLC band behavior. Okay, so this is regarding PLC band. So now I want to shift even a length scale higher. So now I go into the macroscopic scale and really to kind of process simulation. So what we were in particular interested was the material behavior of so-called interstitial free steels. So DC06, which is very often used in the automobile industry. And this material shows interesting effects regarding the hardening behavior. In particular, they show first of all a kind of kinematic hardening behavior, also classified as Bauschinger effect. You can imagine that you have a reverse loading, so you first load it and then load it in the other direction, and you see a different yield point. You don't have the same yield position as you had in your loading, in your unloading. It's loading earlier, it can be deformed earlier. This is Bauschinger effect, and additionally these kind of materials show a so-called cross-hardening behavior. So when you have a orthogonal strain path change, so you make first a plane strain loading, then doing a shear loading onto this, you see this kind of behavior. So what does it mean? Well, you see here a strong stress overshoot. So this one here is the classical monotonic shear loading response of this material. However, when I first do a loading plane strain tension and then doing a shear, I have a much higher yield strength. Well, what is the reason for that? Well, we investigated the microstructure, and what you can see is, this is kind of the loading direction, that you have orthogonal to this very strong and thick dislocation walls. So it's a kind of latent hardening behavior, if you want so. And when I now change the loading direction orthogonal to that, of course these dislocation walls have to be overcome. So they have to be kind of rearranged, destroyed, however you want to name it. And in this regard, you get a completely reorientation or reorganization of your dislocation microstructure, and then of course it fits also the monotonic shear stress-strain response. So we wanted to incorporate this for a process simulation, so we have to do a very phenomenological approach, of course, but micromechanically motivated. So what we did, we formulated a model which includes, of course, first of all isotropic hardening. So you can imagine that you have your yield surface, which is just isotropically expanding. Then you have a kinematic hardening contribution, which means your yield surface is moving. It's not changing, it's just moving in space. And then you have a cross-hardening contribution, which changes actually the shape of your yield surface. Well, we formulated this in terms of this flow potential. We have here, first of all, this S is simply our stress, macroscopic stress, so Cauchy stress. X is our kinematic stress method, where we have an evolution equation coming, kinematic hardening, coming here from, we used the Frederick Armstrong form. Then we have this force order tensor A, which is our initial material anisotropy. For example, it could be for Mises, if it's isotropic on the beginning, or here we used, for example, Hill. And then we have this tensor H, which is our evolving flow anisotropy tensor. I'm coming to that in a second. And then additionally, we have here our isotropic hardening contribution. So very classically, as always done. So our evolving flow anisotropy tensor has two contributions. One contribution coming here from the dynamic part, and one coming from the latent part. And of course, as we saw already in the experiment, the dynamic part we assumed to be 0 because we accounted for that already by the isotropic hardening contribution. So we only had to identify here our latent hardening contributions. And for this, we of course used several tests. So we used classical plane strain tension test, we used shear test, as well as this plane strain tension, and then following up shear test, as well as uniaxial tension to identify our material properties. And we could capture this kind of behavior very accurately, as just identified. And then of course we were able also to investigate our yield surface evolution more closer. Now what you can see here is our classical initial yield surface, so this is for Mises now. And then starting from that, we have a loading path which is going in this direction. We're loading in this. And this is what our yield surface looks during this loading pass. So we have a change then at this point. We're now loading in this direction from there on. And you see directly a completely shift of our yield surface, which is somehow representing this reorganization of our dislocation structure. And by this model, we can now apply this for process simulation. So we did that. Let's continue. Yeah. So we did this with some experiment which was done at the Institute of Forming Technology and Lightweight Construction at the Technical University in Dortmund. So in principle, a deep drawing setup, and this was our demonstrator, how it looks like. So we have different curvatures, different radiuses to have a good comparison for the modeling. So we set up, of course, our finite element model, which accounts, of course, for the die, for the matrix, and also we applied the correct force to actually keep the platine here correctly to account for, also the blank holder force, to account for the correct flow inside of our specimen. So then we performed a simulation, as you can see here. So we have now here our complete forming process, and of course we can measure now our stress level and of course several more features. What we were particularly interested, of course, because we couldn't do it experimentally, how big is actually the contribution from this cross-hardening? This was one of the aspects we looked at. So for this, we, for example, looked here simply of the norm of this cross-hardening tensor, just to have a kind of measurement of this cross-hardening. And then we could, of course, see, okay, there were some regions which have a stronger contribution than other ones. And this could be then used, of course, first follow-up to take, for example, specimen out of that and doing some tensile tests to actually investigate the kind of hardening behavior which this material at this position had. But we could already predict that. We did then, of course, some comparison regarding the shape. As you can see here on the right, we in particular looked in the effect of the spring back in this kind of samples. And at least in the principal shape, we could do that quite correctly. However, here, of course, there was some slight deviation at the outside surface. But at least from the cross-section, we got a very good agreement between simulation and experiment. Okay, so we went, of course, a step further and wanted to see, okay, what might be the effect of this cross-hardening contribution with respect to, for example, its forming limit capabilities. And for that, we performed some Nakajima test. Nakajima test is, you can, in principle, do the kind of specimen in this way. So you cut out certain radiuses, and by that you can generate different stress states inside of your material. Well, you have a very nice choice to actually investigate these different strain states. So starting from uniaxial, so this is a uniaxial stress state, coming here to a kind of biaxial stress state. And what you can see here from the simulation is, first of all, you have in the uniaxial state, you have a much earlier failure behavior, which is also classically known, compared to this biaxial. So we investigated this then, of course, also quantitatively. You see here the punch force with respect to the punch displacement, just for the simulation. For the different radii, you see, of course, for this one it's very low, and then if you increase, it has to be, there's more material, obviously. And interestingly is now the difference between the cross-hardening and the non-cross-hardening model. And what you can see is, in the uniaxial case, there's no difference. But you would not expect any difference also, which I will show in a minute why. But you would expect, in this case, strong differences. And this is also visible, of course, in the simulation. And the cross-hardening seemed to actually increase the forming limit capabilities of the material, at least from a simulation standpoint. Now you can then, of course, go a step further and investigate the forming limit diagram, which is classically done for the production engineers. And here we used now not the Nakajima, we used the Marciniak-Kuczynski test. And by that we could obtain also a similar trend. We did some deterministic and some also statistics, but we always saw that the cross-hardening shows a higher limit, of course, increasing with increasing the ratio. This has to be clearly said. And what is actually the reason why we have here no difference and here we have the strong difference? Well, we attribute this mainly to the yield surface changes. So when you imagine you have a classical isotropic hardening, you have simply an increase of your yield surface. When you have a kinematic hardening, well, you just have a shift of your yield surface, which means your curvature is not changing at all. And when you have this isotropic plus cross hardening, you get a kind of flattening of your yield surface, and from a mechanic standpoint at least, when you have a more flat yield surface, this means you have an increased formability condition. So the extreme would be the vertex. This would be then the extreme. Okay, so to my last point is in principle what we're currently doing. So as I said, I'm working also now at the Helmholtz-Zentrum in Geesthacht, and our main focus is the design or also the development of lightweight integral structures with improved damage tolerance. So here you can see some of our facilities which we have in our department, and we in particular are working on laser joining and laser modification techniques. And of course we always see this from a point, process, properties, performance, so in this triangle, and we want to optimize this in this regard. But we not only want to do that at lab scale, we actually want to do it at large scales, so we really do in conception and realization of lightweight demonstrators for the aerospace industry. So they are then also directly 1 meter long, so we are not anymore at these small scales, so these machines have to work also at these large scales. And one of the things is that we in particular are interested in the damage tolerance behavior, so we test them, assessment, and of course we're doing also simulation, and there in particular I'm coming into play. So my group is called there Residual Stress Engineering, so we're trying to design the residual stress profiles inside of these structures in an optimal way to have this improved damage tolerance. So what we're doing, well, one example here would be the laser beam welding technique. Well, why is laser beam welding interesting at all? Well, we want to, this is an alternative to rivet connections, which allows, of course, lower weight. So here you have a rivet connection, here you have a laser beam welding connection, you directly see there's less material present. And here you see now a laser beam welding process, how it looks in our lab. So we have 2 samples, so we have a butt joint, and we have our laser running over that. So here's our laser beam, we have a kind of melting of our material, and then the material solidifies, and we have a connection between the two parts. So why is laser beam welding in general a nice technique? Well, it allows a lower and concentrated energy input into the workpiece compared to other welding processes. No? So you can do it very concentrated. So what we did there is we set up a process simulation model. So one of my PhD students is currently working on that, which has to account for here a number of different phenomena. So we in particular looked here at the precipitation hardening model. So it was an aluminum alloy 21939, and incorporated all these information into a plasticity model. So the first step which we had to do, as you can imagine, this laser beam welding is quite fast, and we have extremely high temperature gradients. So one of the things we wanted to incorporate was a kind of temperature model. So we used here a very classical temperature distribution to model actually the laser heat input in our model, and we then obtained an analytical formulation based on Green's functions. I avoid now here the equations, and could predict the temperature field then directly for the simulation in a very fast way. So it costs in principle nothing, we can directly incorporate this into in our final element simulation. This is the comparison between experiment and simulation, and here you can see this should be the comparison with respect to a thermocamera. We also had thermocouples, but we saw in the study that actually the thermocouples seem to be too slow. So they're dynamically not accurate enough to actually capture these high gradients which we have inside of our structure. This is of course not in the keyhole, no? So it's not in the fusion zone, it's outside, otherwise it's hard to measure. So in the keyhole you have probably a temperature around 2000 to 3000 Kelvin. Yeah. So then we went to the mechanical part, of course. Yeah. For that, we investigated, for example, some aging curves. So this is now for 6005 out of the literature. Based on Vickers data, we did that also now for 2139. And by that you can get a kind of so-called master curve, which in principle gives you a relation with respect to actually the volume fraction of your precipitants inside of your material in terms of temperature and time. So we used here a model out of the literature, very similar to the Robson model. This is coming now from Muir, from Norway, and this can then be incorporated in kind of a mixture rule, which we used here, which accounts then, of course, for material which is in the complete solute state and in the complete tempered state. And by that we could then investigate first of all the hardness, there's no surprise that you have a much decrease here in the fusion zone region. There's afterwards no hardness. But we were in particular also, because all the precipitants are resolved, you have a complete melting. But we were in particular interested in the residual stress profile. And what you can see is during the fusion process, it first looks like a compression stress state. However, as soon as we have a complete solidified region, we can clearly see there is a high tensile stress region inside of your material. And we wanted to predict this, of course, correctly. And we investigated then experimentally, which we did at synchrotron, at DESI, so with synchrotron radiation. And this was shown here, and we could predict the same in the simulation. In the simulation, only the half is shown because of the symmetry. So this gives a first idea. We are still, of course, developing this model further to incorporate this effect even more on a more detailed microstructure level. Okay, so the last topic I will present is the so-called laser shock peening process. Goal is here to have an improved damage tolerance and design for lightweight structure. So why do we do that? Well, fatigue is one of the main causes of failure mechanism. And when we have a residual stress field, compressive residual stresses, this increases the fatigue resistance. So we need a specific residual stress design. So here on the bottom, you can see now our process in the simulation, hopefully. What you can see here in a second is that the laser, which is moved by a robot, is shooting in principle laser impulse on side of our specimen, and by that we can introduce a kind of shock wave. The process is looking like this. So we have here usually a water layer or a foil. We have our laser pulse. And then this laser pulse penetrate our material. By this, it builds up a plasma. So we have some vaporization of our material, of course. We have here the water layer, which keeps the plasma under this. And then by this, we're introducing a shock wave or pressure wave inside of our material. And what we in particular were looking at, what is actually the influence, for example, of the base layer and of course of the process condition in this process. So, how much time do I have?
2 minutes.
Perfect, yeah, I will do that. So what we did, first of all, we investigated, of course, this experimentally. So here you can see a typical specimen, how it looks like in the experiment. And we investigated this in particular with 2 base layers, one is steel and one is air, to investigate, okay, how big is the influence of that. So this is how our specimen look like. So we have different laser profiles and of course different intensities. And this is a big specimen. So we have one with base layer, one without base layer, one with base layer. And we investigated now the residual stress profile based on hole drilling techniques. Hole drilling is, we measure for that the surface deformation after each increment which we drill. And we can then, based on the integral method, calculate the residual stress deformation. I have clearly to say the assumption here is linear elastic material behavior and that residual stresses are constant parallel to the surface. This has to be clearly mentioned. So we studied then the influence of the base layer. We did the experiments. We obtained here, of course, our residual stress fall over the depths. And you see you have an increase in depths, and then it goes, of course, back to 0 at some point. Laser shock peening is a process which introduces relatively deep compressive stresses. We set up a finite element model for that, investigate then, of course, the influence of the base layer. And what we could show is, well, there was no influence. We could take it, so everything what we did experimentally was fine. Here also some experimental data. So if we stake steel or air, it gives us the same response. So this was now a stage, no influence of base layer. I will skip over this. So we have, of course, taken a Johnson-Cook model in our simulation, and we had to develop a method how to actually calculate now our stresses in simulation to be comparable to hole drilling. So we had to take some average over a surface. We developed this here, and of course, one important question here was how to import the pressure field inside of our simulation. So we used this pressure pulse. And we could identify this on experimental data to have the accurate response of that. We did that for 2198T3, and this should be the last slide on that. So we have the experiment. We set up our new model now. We incorporated here infinite elements because we know there is no influence of the base layer, so we can account for that. We have our 9-shot model. This is enough for the simulation at this point. Then we could incorporate, of course, how is the influence of each of these shocks inside of a material. So this is how the residual stress profile looks afterwards. We did then an identification for 2198 T3. So we have whole drilling experiments and our simulation, which fits very well. But we wanted to see, okay, it's also predictable. And we did that for a different material, in this case 2198 T8, which shows completely different material properties in terms of strength. And yes, we were able to predict the response quite accurately, so there is a faster saturation in terms of the residual stresses of these specimens. And with that, I'm actually at the end. I present you some hopefully interesting works, and I'm thanking you then for your attention and open for questions.
I'm still impressed by the very first one you showed in terms of how well that fit. I'm a believer that computer experiments are most important in showing us what doesn't work rather than what works, but always when you give us a seminar, you show what works. I'm curious what, in terms, because that model, the model you used there wasn't obvious to me. Okay. What did you try before that failed?
Oh, actually, in this case, we didn't try anything before, because what we used is a very classical crystal plasticity model. So this is known since the 90s, I would say. So very classically, we were actually impressed that we could capture this already with this simple model. We were expecting something much more, we would need something much more sophisticated to be accurately predicting this kind of deformation history, but unfortunately we had to say no, we don't need to do any GND kinematic hardening. The simple crystal plasticity, which mainly accounts for the Schmidt stress, that's the main contribution, is already enough we need. This was actually, so in the opposite, we didn't go deeper at that stage because our first results showed perfect agreement, which we didn't expect. We were expecting there had to be some large differences. I mean, I showed you for the ideal plasticity, obviously, and this was also a check for us to see, is this really true what we're getting out here? And yeah, it was the same for us. We were also surprised that we could already accurately predict the deformation and also the orientation gradient field in this way without any sophisticated model. This is really very classically known for, it has 24 glide systems, sure, it's more than a classical phenomenological model, but to account for these orientations, and also we investigated, for example, at that stage, what kind of glide systems do you need to incorporate in BCC, because this seemed to be not obvious. We also tried 48 and we also tried 12, and all these are possible. For 24 we got the best results. For 12, either if we take the 110 or the 112, there were differences, clearly, but both were also quite accurately already describing that. One assumption I have to say, which we took here, is that the 110 and the 112 direction, the glide systems are equivalent. So we took the same parameters. In the literature, sometimes they say they are 5% difference. We didn't account for that, to say that clearly.
Thank you. That was a very impressive array of computational materials engineering. I have a small question about the welding problem.
Yeah.
So in that problem, if I understood right, you weren't trying to model the melting and solidification process. You just assumed that was just a moving heat source. No,
actually we do modeling, of course, we're not specifically doing the fluid flow, to say that clearly. So we assumed an incompressible element for this, and we of course decreasing the properties to a kind of melting stage. Okay. So we have a kind of Newtonian fluid at this point, but we assuming still, because we're doing finite elements, that it's incompressible, because this was our first problem we had. We had extremely high deformation in the melting zone, because no stiffness, if you want to say it so. So for that we needed an incompressible one, and by that we could predict that. But we're not further investigating the the melting.
Yeah.
We are
so you're not investigating the melting. That might have some impact on the shape of on the weld.
We will do the solidification actually. So the melting, we're starting with the melt. We assume that's perfectly, and then doing the solidification in terms of grain growth. We will do that. Yeah. At this stage, it's purely phenomenological. Absolutely.
In the models that complex like yours, one of the main challenges I found in my previous life was material parameters.
Yes.
And in particular in development of residual stresses, when there is a part that is flowing and then it changes the properties with temperature, that it is very tough to get. So where did you get this
well,
data
I mean, currently at the laser beam welding problem, if you're referring to that, we have of course taken some literature data in terms of how is actually the material flowing, so like a Newtonian fluid, which is a very simple assumption, I have to say. And we attributed this here mainly to the precipitants. So this was one of our key assumptions here, which might be not 100% true, but we want to go there for a next step to investigate that, for example, with phase field modeling, to have a more closer understanding how the properties then are actually looking like, and based on that then to identify actually macroscopic properties in this regard. But material properties is always a big issue.